Yeah, so group isomorphism problem, it's a joint work together with James Wilson. It appeared a couple of years ago in 2022 in FOCS, but it's a very nice result that's suitable for short talk, so I thought I'd report about that. So, group isomorphism problem, as you probably know, is a family of problems. You know, it's problems around the question, here are two groups, are they isomorphic? Right? They come in different flavors, these questions. You might just be interested in decidability. You might be interested in, you know, can I solve it with a certain complexity, or is there actually an algorithm with it, right? Or you look at it from a practical perspective, like in group theory, for example, where you actually want to compute isomorphisms or decide isomorphism of groups. So this talk, we talk about more of the theory side. I consider the group isomorphism problem in the Cayley model, where the input are two multiplication tables of groups, or actually two n times n tables, with entries in 1 to n, and it decides whether these tables describe groups and whether they are isomorphic. So that's the question. And obviously, if you do computational group theory, you might find this very boring, because it's very unuseful in practice, obviously. We don't work with multiplication tables, right? But it's still very relevant. Firstly, it's clearly in the class NP. You can readily verify whether you have an isomorphism if someone presents it to you. It's not known to lie in the class P, so it's a good candidate for an NP intermediate problem. Secondly, it reduces to graph isomorphism, and there has been some recent progress. A new quadruple polynomial time algorithm by Babai, 2015 and the following years. And turns out group isomorphism has in general the same complexity bound, so it seems to be an obstacle for improving graph isomorphism. And lastly, on the practical side, you know, in computational group theory, often you want to have small input sizes, usually like log n. And you want algorithms that work polynomial in log n, right? However, in practice, there isn't often even an algorithm that runs in polynomial in the time of in the size of the group. So there might be one reason to say, well, maybe let's first get a polynomial time algorithm in the group size rather than immediately going for log n. Pascal Schweitzer gave a very nice comparison. He said that getting polynomial in the group size is shooting for the moon, and it makes seem getting polynomial in log n shooting for Mars. So maybe you should first solve a slightly easier problem. All right, so what is known? Again, this is highly incomplete, just want to give you a flavor of what has been done. So there's the up-to-date general complexity bound for general groups due to Miller, and he gives credit to Tarjan. James already mentioned this bound here, and it's really just a brute force approach. You pick a small generating set, you look at all possible assignments, and you check whether there's an isomorphism or not. And funny enough, this bound really has been resistant over all these decades. So usually progress has been fragmented into subclasses of groups, and then people made progress. So I'm not going through the whole list here for time reasons, just to show some works here that have shown up, and I will mention a couple of these people later as well. What I do want to point out is, however, that you look at these complexities and you see, aha, a billion groups can be done in time O of n. Then you wonder maybe, how is this possible? You know, reading the whole input does require you to do n squared log n, and even doing a multiplication on a Turing machine does require n squared log n. So what's the secret here? Well, some papers use different computational models. You know, some use the promise hierarchy where you might not have to read the whole input. You are promised that you have a group. Sometimes they use the random access model where, you know, they just cost a constant cost for memory access and group operations and things like that. So it's just highlighting that when you pick up a paper and check a complexity result, you have to be really careful what model they use. You know, there might be different assumptions. All right. So what have we proved? Well, my abstract and title gave it away. We basically showed that group isomorphism is easy for almost all group orders. So what does that mean? Well, it means there's a dense set. Well, what is the dense set? Dense set of positive integers is a set such that this limit here goes to 1. So it's sometimes also called the natural density. So there's a dense set of non-negative integers, our group orders, such that when you hand the computer two tables, n times n tables with n being in that set, then there is an algorithm that decides whether you have groups and whether they are isomorphic. And the complexity is basically as good as possible because it's O of n squared log n to some c. That's pretty good. A couple of comments are in place, and that's really important. We say almost all orders, not almost all groups, right? well known that all the groups don't distribute evenly among all the orders. You know, there's one group for prime orders, but there are many, many groups for prime power orders. So we just consider orders, not all groups. Secondly, but not surprisingly, our set of orders excludes orders that have large powers of a prime as a divisor, and large with respect to the original size n. So this theorem sort of supports this conjecture that P-group isomorphism is really the bottleneck of group isomorphism, because for all those orders it's very easy. And then also on the positive side, for some classes of P-groups, there has been some recent very impressive progress, most notably by Sun and Ivanov, Sun and Sao. They have looked at large classes of P-groups and proved also very good complexity bonds. So maybe altogether this could all be used to prove that maybe the average case complexity is not too bad. All right. Another result I want to briefly mention is we also have in the same complexity an algorithm that checks whether the input is actually a Cayley table of a group. They're obviously decided that it can easily do it, it's just the complexity bound is pretty good. Most results in the literature use n cubed. There's a paper that has the same complexity listed, but they actually use constant time multiplication, which we don't. So this means that our algorithm really works in this complexity and it avoids the promise hierarchy. We don't have to promise that what we hand over is really a group. And along the way, we also set up a data structure that allows us to compute with the group a bit more efficiently. All right, so how do we do this? So the main purpose of this talk is just to describe the mathematical background that allowed us to do this. So how do we do this? Well, usually there are two different types of problems that play a role. Either the group theory could be too hard, or big number theory suddenly shows up. Well, of course, for the Cayley table input, number theory isn't such a big deal, but really, we separated those two problems here. So we focused on group orders that allowed us to say that every group of this order always splits into a sort of semi-direct product, H and B, where H basically encapsulates the hard group theory, whatever that means, and B contains the big number theory, so all the large prime divisors of the order of G. And we do it in such a way such that the size of H is tiny compared to N, so brute force methods work. And the number theory here, well, it doesn't really matter so much because the group structure of B is very, very easy. Well, spoiler alert, it'll be cyclic. So that's the idea. So let me briefly talk about the number theory side. So this slide may be a bit technical. It lists the definition of our set D, but just maybe try to get a gist of how this works. It's all based on the fact that most integers have many distinct and large prime divisors. It's a result of Palfi and Erdős. So Palfi and Erdős basically say that if you look at the set of all positive integers that factorize into S times L, small and large, such that S contains all small prime divisors, and small means less than log n, and large contains all large prime divisors, then this set is dense. And you can also assume that this is square free, and then you can add further assumptions. You can assume that every divisor of L here is what's called isolated. I'm not going into the definition here. The set is still dense. You can add the assumption that L is at most this many prime divisors, so this follows from Hardy Ramanujan, that the set is still dense, and then we needed yet another condition, namely that those other prime powers that show up here are also small. And it's still dense. So this is our set, so it's highly technical, as I said, but to give you an idea of how dense it is, well, if you look at up to 10 to the 9, it's like 78% of all numbers are in this set. So this is the number theory. The group theory, well, follows from the number theory, so if you have a group of that order, S times L, then we can prove that it really splits. We have a normal Hall pi n subgroup, where pi n is a certain subset of the prime divisors of L, so the large primes, and there's a complement H, such that B is cyclic, and H is tiny. So that just follows from our restrictions that we impose on the order. And this is really the backbone of our algorithm, the mathematical backbone of the algorithm. If you have two such groups, then of course the necessary condition for isomorphism is that the small subgroups are isomorphic, which is just checking that the size is the same. And that the complements are isomorphic, which is really brute force because these groups are tiny. And once you have identified these parts, since H is small, you can also check isomorphism of the corresponding semi-direct products. So let's That's really it. So I've brushed a lot of things under the carpet. This is really just a mathematical background. Of course, we had to describe how do we get generators for B, how do we get generators for H, and how do we do all these things. So this is the technical part of the paper, which I haven't really talked about.
Okay, for this.
Almost done. so we, it's a very simple algorithm. We got some feedback from colleagues, obviously, as well, and it was pointed out to us, it's nicely summarized by this comment here, that this Strauss group isomorphism is not only solvable efficiently for most group orders, but also by a very simple algorithm, because it's really as simple as it is. That's all. Thank you.